So today we're continuing on with factoring. And this one here, as you saw on the note sheet, is special factors, special types of factors. And it's not that they follow a different rule or different concept. It's just these are special cases that work out well. And we've seen some of these. And they just have kind of some special properties to them and how they factor and how they work out. Now, the first type, I mean, we'll look at these here. I'm going to spread this across 2 days. We could probably get this all done in one, but I'm going to take my time and do 2 days with this. Now, the first type that we're going to look at here are special in just how they end up factoring out, but we're not going to treat them any differently. Because this here, 4x squared minus 4x plus 1, there's a method that we could go about doing, and I could show you how to factor these, but it's not any more easier or simpler than doing it the way we've been doing it. By first looking to see, is there a greatest common factor between these 3 terms? Okay, so there's not a greatest common factor between these 3 terms here. So we'll move on to our second step, which is our 2 sets of parentheses with 3 spaces, like this here. Our third step is to find the signs, and since the third term is positive, the signs are the same and they match the sign of the middle term, which would be negative and negative. Now the fourth step is to find the factors of the first and third term. And we normally tackle the first term, 4x squared, we'll find the factors of it. Wait a minute, what are the factors of 1? 1 and 1. There's 1 set of factors, so I kind of jumped to it because, well, I know that there's 1 set of factors, so it's a little bit easier to do. Well, 4x squared's factors, so we know it's going to be x and x. Now we just need to find the factors of 4. Well, 1 and 4 and 2 and 2. Which set of factors do we want to try first? 2 and 2. Let's try 2 and 2 first. So any questions on what we've done so far? So we can distribute 3. Well, 2x times negative 1 would be, and negative 1 times 2x would be negative 2x, which gives us negative 4x. Isn't that what we wanted? Yeah. Mm-hmm. And that's it. So this is our answer. I'm going to erase this here. Now you might be wondering, why would we consider this special factors? Why would this one here be listed under the term a special factor? Well, what do we have? We have 2x minus 1 times 2x minus 1. Well, both of those are the exact same, aren't they? So really, the factors for this are 2x minus 1 squared. If we wanted to write it simpler, we could write it as this here. So that's why this one here is considered a special factor, because the factors of the polynomial is pretty much the same thing. It's being multiplied by itself. So there are methods for figuring this out and seeing, okay, is this a perfect square trinomial, which is what they call these here, perfect square trinomials. But it's not any faster to kind of go through the process of one figuring out, is it a perfect square trinomial, and will it work out this way? So it's a little bit easier just to go through our normal steps and factor it this way. So let's look at this next one here. 16b squared minus 40b plus 25. Well, again, there's no greatest common factor between the 3 terms. So we can go to our 2 sets of parentheses with 3 spaces. Now, because the 25, the third term, is positive, the signs are the same and they match the sign of the middle term, which is going to be negative and a negative. Now we need to find the factors of 16 and the factors of 25. One of the factors I do know already is going to be So we are going to have b and b in the first term. Now the factors of 16, well, we have 1 and 16, 2 and 8, 3 doesn't work, but we have 4 and 4. 25 is 1 and 25, and well, 5 and 5. So looking at these sets of factors, so for the first set of factors, for 16, which ones do we want to try first? 1 and 16, 2 and 8, or 4 and 4? How about 25? 1 and 25 or 5 and 5? Let's try 5 and 5. And the last thing we need to do is we need to check. 2b times negative 5 would be negative 10b. Negative 5 times 8b would be negative 40b. Well, this gives us negative 50b. Well, that's a little bit too big. It's a little bit too big for what we want. But we can't switch the 5 and 5, because if we do, we still get the same thing. Now, we could go 1 and 25, but I have a feeling 1 and 25 is not going to get us anywhere closer, because 5 and 5 is already too big. Yes? So let's switch out the 2b and 8b. So that one. 4 and 4? 4b and 4b. Now, if we try this one here, well, 4b times negative 5 would be negative 20b. Negative 5 times 4b would be negative 20b, which would give us our negative 40b that we wanted. So these here are our factors. And that's it. That's all we have to do for this here. Bless you. So this here is the last one that we'll look at this type, these perfect square trinomials. And we look at this here, there's not a greatest common factor between 100, 180, and 81, all three. Because there is a greatest common factor between 100 and 180. And there's a greatest common factor between 180 and 81, but there's not one that's consistent across all three. So we can move on to our two sets of parentheses with 3 spaces. Now, because 81 is positive, the signs are the same, and they match the sign of the middle term. So here they're both going to be positive. So I feel most of y'all are getting to this point pretty easily. Two sets of parentheses, we see that they're both positive, x and x. Now it's looking at the factors of 100 and the factors of 81. Well, the factors of 100 are going to be 1 and 100, 2 times 50. Well, 3 doesn't work, but 4 does, 4 times 25. 5 times 20. 6 doesn't work because 2 and 3 didn't. 3 doesn't work. 7 doesn't work. 8. 1 and 20 doesn't work. 9 doesn't work, but 10 does. It'd be 10 and 10. Now, 81 is 1 and 81. 3 and 27. And 9 and 9. Most likely, if 9 is a factor, 3 is probably going to be a factor. There's a good chance. Now, looking at these here, which factors of 100 do we want to use? 10 and 10. How about the factors of 9 or 81? Well, 9 and 9. And it's kind of, this one here is a little bit leading. It kind of gives us a hint because they're special factors. Most likely we're going to use the set of factors that are the same. But if we're talking about the test, it'll be, won't always be the case, but it could be. 10x times 9 would be plus 90x equals, and we kind of, and like I was just saying, I mean, it's leading because they are special factors. We're going to use the ones that match up. Now on the test, I would highly encourage you all to still check it just to make sure. Because again, checking these and making sure you got the middle term correct is helpful because again, it's almost a way to make sure you got the correct answer. Any questions on this here? We good with this here? Okay. Now that leads us to this here. This next type that we're going to look at are these here. This here, so n squared minus 25. Now these have a special name too. This is the difference of perfect squares. Because n squared is a perfect square. It's something times itself. N times n. Is 25 a perfect square? Yes. It is 5 times. So we signify this as a difference of perfect squares. Now when we covered this in the fall, I said this one here, these types, the difference of perfect squares, are probably going to become your favorite to factor out of all of them. Because for the difference of perfect squares, a squared minus b squared, when I have two things that are squared and they're being subtracted, it factors every single time to a minus b times a plus b. So if I really wanted to kind of write it out like this here for our problem, we'd have what? Well, it'd be n squared minus, how would I rewrite 25 as something squared? 5 squared. So that really, to get it in this form, a squared minus b squared, we could see it as n squared minus 5 squared. Well, a in our case here is n, and b is what? 5, yes? So if we factored this, kind of following this pattern, a minus b times a plus b, well, a is n and b is 5. This would be n minus 5 times n plus 5. That's it. That's why I said these difference of perfect squares are nice, because if I can see n squared is a perfect square and 25 is a perfect square, whatever those are, those numbers, add them, subtract them, we're done. Because it follows that pattern every single time. That's why these are kind of nice, because I'm not having to look at the different factors of the first term and the second term. The addition, subtraction, oh, okay, well, they're 2 being subtracted. They're both perfect squares. Boom, boom, done. So let's look at this one here. We have 16n squared minus 9. Well, is 16 and n squared perfect squares? Well, 16 is 4 times, n is just n times n. Is 9 a perfect square? Yeah. It's what? 3 and 3, yes? So if I wanted to, I could say that this is 4n squared minus what? 3 squared, yes? Because if I rewrote them as squares, so it'd be 4n minus 3 times 4n plus 3, if we're following that pattern. Now, y'all could watch this here, because I'm going to erase this and do this again. Now, say I didn't remember that pattern. I'm like, okay, well, there's not a greatest common factor between these two terms, correct? Okay. 2 sets of parentheses was our second step. The third step was to find the signs, yes? But we don't have a real third term. But kind of this last term is what? So the signs are? So it didn't matter what the middle term was. Then we could go through the factors of the first term, and we'll settle on 4n and 4n. And the factors of 9 would be 3 and 3. And we can still get there using our normal steps. But these here, if we notice that it is a difference of perfect squares, two perfect squares that are being subtracted, we can kind of jump to the answer. That's why these are nice. Questions on this here? Four m squared minus 25. 4m squared minus 25. Is this a difference of perfect squares? Because 4m squared is perfect squares. So, and 25 is a perfect square, so we know we'll have plus and minus. So what would 4m be? 2m, and then we would have 5 and 5. Yeah, because I did that on the first few to kind of so you can see how it broke down. Yes. So that's what we end up getting here. That's why this is a little bit nicer. I used the square so that we could kind of use the a squared minus b squared is equal to a minus b. A plus b, so we could see how that wrote in. But once we get this pattern, it's almost we can jump to it. Okay, let's look at this one here. A to the fourth minus 9. Is this a difference of perfect squares? Okay, so I'm going to write this out since we're not going to jump through it. So 9 would be what? 3 squared. How can I rewrite a to the fourth as something squared? Because we could say a to the a squared squared, powers of powers, multiply. Because a squared times a squared is a to the fourth, yes? So we can do this following the pattern. It would be a squared minus 3 times a squared plus 3. A to the 8th power wouldn't work. Well, it would, actually. We could say a to the 4th squared, and we can do it that way. As long as we can rewrite it as a power squared, number to a power squared, then we can do this here. Because 8 works, 6 works. I mean, most of them would work, as long as it's even. Are there questions on this here? Ooh, I like this one better. I like this one better. X to the 4th minus 81. So this is similar to what we just did. Because I could rewrite this as x squared squared minus what? 9 squared. Yes? So what would that be? We would have what? X squared, well, minus 9 times x squared plus 9, yes? Are there questions on this here? We're understanding how this works, yes? So, yes. Because if it says to factor this completely, because again, what did we use to get from, well, not from here to here? We used the difference of perfect squares, yes? Because, I mean, anytime we have a difference of perfect squares, we can factor it, yes? Do we have any difference of perfect squares up there still? This is still perfect squared. X squared is a perfect square, and 9 is a perfect square, yes? So we can factor that again. Because this here, x squared plus 9 does not work. But x squared minus 9, you'd have what? Because our x squared minus 9, a and b would be x and 3. Well, it's not that it can't be factorable, it won't have real factors. It would be imaginary terms. As if I remember correctly. As if we wanted to factor it, it'd be x. It'd be this here. Because you'd almost have to solve it, set it up x squared plus 9 is equal to 0. Because we would minus the 9 from both sides. X squared is equal to, and when we square root it, we get x is equal to plus or minus. We went over I when we talked about quadratics. So since it's a plus, it doesn't have real factors. So we don't worry about factoring it. We'll leave it as this here. Because having x plus 3i and x minus 3i, especially when we talk about radical functions, isn't going to help us any. Because we're really trying to see what do we need to do to make them equal. Make them denominators be the same. Find out what values of x we cannot have. Or what values of x will make the solution undefined. And I'm going to stop there. I know we've got ample amount of time today, but I want to stop there because tomorrow, again, I know we could do this in one day, but I'm just going to go on and take our time and do 2 days for this. We'll do sum and difference of perfect cubes, which we had the dating story that we did once for the remembering the signs. And then we'll do factoring by grouping, or greatest common factor twice for 3 times.